Hi Calculus. In today's video, I'm going to talk to you about the power rule, and I'm going to give you a few examples and a quick justification. And I'm not going to prove the rule in this video, and I'm just going to give you some bare bones on how to work it. This will be enough to get your homework done, and I'm going to make a series of videos after this going really in depth into the power rule and how to prove it. That'll be really interesting and entertaining, I hope, and a good distraction if you need some distracting today. But they're not vital for the course. So I wanted to first talk to you about the power rule. This is copied straight from your textbook. It says if n is a positive integer and f of x equals x to the n, then when I take the derivative, this is what happens. So let's do an example here. Oops. Great. Okay. So let's do an example using this power rule. So let's say we have f of x equals x squared. So in this case, n is equal to 2. So the power rule says f prime of x is equal to n x to the n minus 1. And in this case, n is 2, so that would mean this is 2x to the 2 minus 1, or 2x. So then f prime of x is equal to 2x, and that's our final answer. Last week I had you calculate this the long way using the limit definition. Hopefully you don't hate me for making you do that now that you see how easy it could be. Let's do a second example. Example 2. Let's say I have the function, and I just tell you this. I say find the derivative of x to the 14th power. I don't say y equals or f equals or anything. I just say find the derivative of this. You can actually use here this second definition here, where they say d over dx of x to the n equals nx to the n minus 1. Okay? So what this means, this d over dx, that's saying you the derivative, the change in x. So it's saying the derivative of this x to the n equals nx to the n minus 1. And you could use that notation too if you wanted. And so let's go back here to our example. So I want to take the derivative with respect to x of x to the 14th power. And I know that that's going to be nx to the n minus 1, where n is equal to this right here. So n is equal to 14 in this case. So my derivative will be 14x to the 14 minus 1, which will be 14x to the 13th power. And this is enough to get you through the day when it comes to the power rule. There's one more fun fact I want to share with you. And this fun fact is also known as the constant multiple rule. Suppose I give you this example, for example 3, and I say f of x is equal to 4x cubed. Find f prime of x. You might wonder how it is exactly I'm supposed to handle this. Oops, it's supposed to be the highlighter. Sorry, gang. How am I supposed to handle this constant 4? Well, good news for us. Recall the derivative is based on limits. So we can use limit laws. I'll show you what I mean here. Suppose we were doing this the long way. We were saying f prime of x, and the definition for that is the limit as h approaches 0 of f of x plus h minus f of x all over h. And so we want to use that with our function here. So I'm going to go ahead and plug it in. So then we would get the limit as h goes to 0 of 3 times x plus h. Oops, not 3. Sorry, guys. I forgot what I was doing. It would be 4 times x plus h to the third power minus 4 times x to the third power all over h. And I can use my algebra here to factor this out and look at it this way. Limit as h goes to 0 of 4 times x plus h cubed minus x cubed all over h. And then here I can use my constant multiple law to actually bring this out like so. So I get 4 times the limit as h goes to 0 of x plus h cubed minus x cubed all over h. And now what I have here is just the definition of the limit. So I can say this is the same as 4 times, or I'm sorry, not the definition of the limit, it's the definition of the derivative. So this is 4 times the derivative of x cubed what this means for us is that in our example, when I have f of x equals 4x cubed, and I want to find f prime of x, I can just do this as 4 times the derivative of x cubed. So that's going to be, using our definition here, n times x to the n minus 1, and n is equal to 3. The reason n is equal to 3 is because that's the exponent we have on our variable of x here. So then this becomes 4 times 3x to the 3 minus 1, which becomes 12x squared. And that would be our final answer. I'm going to do one more example there of that kind. I forgot what example we're up to. Is this example 4? Yeah, it's example 4. So let's do one more example of something like that. Let's say I had g of x equals 1/2 x to the 5th power. And I want to find g prime of x. And I know that's going to be 1/2 times n x to the n minus 1, where my n is equal to 5. So I get 1/2 times 5x to the 5 minus 1 power, and that gives me 5 halves x to the 4th power. Nice, right? We can also use this for rational exponents. So suppose I have a function h of x equals the 5th root of x, let's say. Well, if I change the notation here and I write this as x to the 1/5 power, I put it in rational notation instead of radical notation, I can use this same rule. So in this case, h prime of x is going to equal n times x to the n minus 1. And here, n is equal to 1/5. So I'm going to go a little bit slower because this involves fractions, and I know how you guys feel about that. N minus 1 would then be 1/5 minus 1, which is 1/5 minus 5 over 5, which would be -4/5. So this involves some reminding you about exponents and the rules of exponents, but I think you guys will get the hang of it. So here, h prime of x is going to be n times x to the n minus 1. So it's going to be 1/5 x to the -4/5 power. And you remember in algebra, it's not considered fully simplified if we have a negative exponent. And the way that we resolve that issue is we take the reciprocal here. So we have x to the -4/5 over 1, and we're going to take the reciprocal. So now we have 1/5 times 1 over x to the +4/5, which you could put in radical notation if you like, and you could say 1 over 5 to the 5th root of x to the 4, or you could say 1 over 5 times x to the 4/5. Either one is good with me. These would both be acceptable final answers. There. Great. You can also use the product rule when you have a negative exponent to begin with. I'm sorry, did I say product rule? I meant power rule. Power rule with negative exponents. I don't know if you can hear, but my dog just jumped on the bed and is panting heavily. So we have power rules with negative exponents. So here's an example of that. Suppose I had a function h of x equals 1 over 2x squared. So I'm going to rewrite this as h of x equals 1/2 times x to the -2. Take a second and convince yourself that those two are equivalent statements. Now I want to find h prime of x. And I know that's going to be 1/2 times n x to the n minus 1, where my n is equal to -2. So then n minus 1 would be equal to -3. And my derivative will be 1/2 times -2 x to the -3rd power. And I just have to simplify here. 1/2 times -2 over 1 just gives me -1. And x to the -3 becomes 1 over x cubed. So then my derivative here would be 1 over x cubed. Final answer. A nice thing about this video is if that was a little bit too fast for you, go ahead, rewind, and watch it through another time. All right. So that's it for this video. Like I said, this will get you through using this power rule. Will get you through your homework, and it'll get you very far in calculus. So if you want to take a little pandemic break and not think about the power rule anymore, you can. You can just roll with it and use it for the rest of the class. I encourage you, if you have extra time or if you need some extra distraction, to go ahead and watch the next video in the series about the power rule, because I go through some stuff that I think is really interesting and fun. So I hope to see you in the next one. And as always, I want you to be well, be safe. I miss you guys. I miss you. I hope you're well. I'm going to try in the last little bit here to do something cool and see if I can show you what I'm looking at. This is my little baby. She's sleeping on my lap while I do this video for you guys. Cancel. I hope that turned out. All right. Stay well, guys. I'll see you in the next